Suppose you mix hydroxide with methyl bromide. What will happen is they will react. A spontaneous reaction ensues. Well, what is the reaction? What are the products? The products are methyl, alcohol, and bromide ion. Let's examine the change in structure that's occurred in this reaction. If you look, you can see hydroxide, one of the reactants, has come in and replaced the Br. The hydroxide takes the place of the Br, or we say hydroxide substitutes for Br in this reaction. This reaction is an example of what we call a substitution reaction. A substitution reaction is defined as a reaction where an atom or group of atoms substitutes for a different atom or group of atoms of a reactant molecule. Now there are some terms. The hydroxide that comes in and replaces the Br is called an entering group. The Br that gets replaced is referred to as a leaving group. The organic reactant containing the leaving group is called the substrate. Now, some other terms. The hydroxide entering group here is called a nucleophile. The carbon atom that the nucleophile bonds to is called an electrophile. A nucleophile is a species with an atom having one or more lone electron pairs. In reaction, the nucleophile binds to an atom, namely the electrophile, by donating a lone electron pair to the atom. Electrophile is an atom of a reactant that bonds to a nucleophile by accepting a lone pair from the nucleophile. And you take a close look, you see that's what's going on here. The hydroxide comes in, one of its lone pairs gets donated to the carbon. The bond to the Br actually breaks off. That pair of shared electrons breaks away from the carbon and moves with the Br, and the Br breaks off as a bromide ion. Because the entering group is a nucleophile, this reaction is called a nucleophilic substitution. Nucleophilic substitution reactions follow two basic mechanisms. Let's examine them. One mechanism is called SN2. Now in this mechanism, the nucleophile bonds to the substrate at the same time that the leaving group departs. That is, the nucleophile comes in, starts to form a new bond to the carbon by donating an electron pair, and at that same time the leaving group with its pair of electrons breaks away from the carbon. It's all a one-step process. SN2 refers to the following. S stands for substitution, N for nucleophilic, and the 2 refers to the fact that two molecules are reacting together in this single step of the reaction. That is, the reaction is bimolecular, and that's what the 2 refers to. In the second observed mechanism for nucleophilic substitution, this is called an SN1. This is a two-step mechanism. In the first step, the leaving group breaks away from the carbon, and that is the slow step of the two steps. As the leaving group breaks away with its pair of electrons, it forms a positively charged carbon intermediate. It's called a carbocation. is a +1 charge. Then in the second step, and it's the fast step, the nucleophile comes in and forms its bond to the positive carbon of the carbocation to form the final product. Here SN1 refers to the following: S for substitution, N for nucleophilic, and in this case the 1 unimolecular. That is, in the slow step of the reaction, one molecule and one molecule only reacts. There is no nucleophile reacting here. It's patiently waiting for the carbocation to form, and then in a completely different second step, the nucleophile reacts with the carbocation. Since there's only one molecule reacting in the slow step, this is a unimolecular reaction, one molecule reacting SN1. Now, in our experiment this week, we're going to examine the effective structure on the rate of an SN1 and SN2 reaction. As we discuss this, we're going to use alkyl halides as our substrate in the nucleophilic substitution reactions. Alkyl halides are classified according to the classification of the carbon bearing the leaving group. Here are some examples. Here we have the alkyl halide ethyl bromide. The carbon to which the bromine is attached, this is the leaving group, is a primary carbon. Thus, the alkyl bromide is referred to as a primary alkyl bromide, primary alkyl halide. Here's another example. This is tertiary butyl chloride. The carbon bearing the leaving group, the chlorine, is a tertiary carbon, and consequently we refer to this as a tertiary alkyl halide. In general, we find in nucleophilic substitution reactions that a regularity is observed. SN2 reactions, that is, reactions following an SN2 mechanism, follow this order. A methyl substrate is the most reactive of all the possible substrate. It's most reactive, more reactive than the primary substrate more reactive than a secondary substrate, and the secondary substrate is a tertiary. Of the series, methyl substrate is the most reactive, tertiary substrate is the least reactive. Now, in SN1 reactions, that pattern is completely reversed. SN1 reactions follow this order. Of all the possible substrates, the tertiary substrate is in fact the most reactive. More reactive than secondary, the secondary more reactive than primary, and the primary more reactive than methyl. Here, a tertiary substrate is the most reactive, and the methyl substrate is the least reactive in a substitution reaction following an SN1 mechanism. Let's explain that. First, the SN2 process. Evidence indicates that there's a strict mutual orientation of nucleophile and substrate that takes place in the reaction. Right? In the reaction, the nucleophile wanders up and comes closer to the substrate. It does it from a specific side of the substrate. It comes in from the side opposite the leaving group. We refer to the side opposite the leaving group as the back side. The same side as the leaving group is called the front side. It comes in from the side opposite the leaving group. It forms a bond to the carbon, and at the same time the bond to the leaving group breaks. Goes through a transition state, ultimately resulting in the products. A new bond formed between nucleophile and carbon, and the bond between the leaving group now completely broken. The important thing for us to see is this mutual orientation that occurs. The nucleophile is very choosy in that it approaches and bonds to the carbon of the substrate from the back side. Now, how hard or easy the SN2 reaction is, it's a matter of how easily the nucleophile can form a bond to the electrophilic carbon. How easy the nucleophile can access that electrophilic carbon. It's easiest for the nucleophile to bond to the carbon if there are no carbon groups, that is, alkyl groups attached to that carbon, our target atom. Such carbon groups block the nucleophile's entryway to its target. Obviously now, the more alkyl groups there are bonded to the target carbon, the more difficult it is for the nucleophile to reach its target. The fewer alkyl groups that are bonded to the target carbon, the easier it is for the nucleophile to reach its target. Alright, thus, the easiest and fastest SN2 reaction is between a nucleophile and a methyl substrate. The methyl substrate having no carbon groups attached to the carbon. Now, the hardest and the slowest reaction is between a nucleophile and a tertiary substrate, a substrate with 3 alkyl groups attached. A substrate with 3 alkyl groups presents what we refer to as steric hindrance to the bonding of the nucleophile to the substrate. Therefore, we see the observed order of substrates in an SN2 reaction as follows: the most reactive methyl, more reactive than primary, primary more reactive than secondary, secondary more reactive than a tertiary substrate. Let's now discuss the SN1 mechanism. There's a natural impediment for a nucleophilic substitution reaction that follows an SN1 mechanism. Now, the reaction has to produce a carbocation intermediate. This intermediate has a very high energy and it's hard to form. Alright, however, a carbocation is easier to form if there are electron donating groups attached to the positively charged carbon atom of the carbocation. That's because such groups will stabilize the positive charge and lower the energy of the carbocation. Here's some new information. It turns out that alkyl groups are electron releasing. They're relatively good electron releasing groups. When attached to a positive carbon of a carbocation, they feed electrons to it. Now, what's interesting is that all alkyl groups are pretty much about the same in terms of the efficiency with which they donate electrons to a positive carbon. A methyl is about as efficient donating electrons as a isopropyl group. However, you can see it logically follows, though, that the more alkyl groups, the more electron-donating alkyl groups that are attached to the positive carbon of a carbocation, the greater the stabilizing effect on the carbocation. Thus, the most stable carbocation is a tertiary carbocation. That is, a carbocation with 3 carbon groups bonded to the positive carbon. Consequently, we see the following order of carbocation stability. The most stable carbocation is a tertiary carbocation with 3 carbon groups attached to the positive carbon. Tertiary carbocation is more stable than secondary, secondary more stable than primary, primary is more stable than a methyl carbocation that has no electron feeding groups attached to the positively charged carbon. Now, because a carbocation is formed in the slow rate-determining step of an SN1 mechanism, a tertiary substrate, of course forming a tertiary carbocation, is the most reactive substrate. A tertiary substrate reacts the fastest in an SN1 mechanism because it forms the most stable, easiest to form tertiary carbocation. Thus, we find the following observed order of reactivity of substrates in an SN1 mechanism. This: of all the possible substrates, the tertiary substrate is the most reactive, tertiary more reactive than secondary, secondary more reactive than primary, primary more reactive than a methyl substrate. The last point now that we're going to consider is the effect of the leaving group on substrate reactivity. The reactivity of a substrate in a nucleophilic substitution reaction is affected by the nature of the leaving group. Now, some leaving groups are easily displaced by a nucleophile. We refer to them as good leaving groups. However, other leaving groups are not easily replaced. They're really reluctant to leave, and we call them appropriately bad leaving groups. For now, here's a list of good and bad leaving groups. Good leaving groups: chlorine, bromine, iodine. Note that these are the lower members of the halogen family. Bad leaving groups: fluorine and OH. The fluorine is the top member of the halogen family of elements. In this week's lab, we will test the leaving group ability of Cl versus Br in nucleophilic substitution reactions.